Okay, so here we go on to section 8.4. The official title for this section is Partial Fraction Decomposition. Now, talk about an intimidating mathematical word, partial fraction decomposition. But really, it's not that bad. So before I get into it, I'm going to tell a quick story. What are we doing here? I'm supposed to be in black. So we're doing partial fraction decomposition. And first, I'm gonna tell a quick story. Now, one of the things that happens when you have kids is that everybody wants to help, and sometimes the help is helpful, and sometimes the help isn't really that helpful. Well, when my son was first born, my dad came to visit, and I was doing something with the baby, and my dad was just trying to be helpful, and he noticed that on my desk I had this integral equation that was some fraction, something like this dx, and then plus some other integral. There was also some fraction dx like that. And what my dad did is said, well, I can write this as one integral. So he wrote it out and wrote it kind of like this, and there's some stuff plus this other fraction here, and he combined these two integrals into one integral, just the sum of the two. And then he realized that, well, if you just could make a common denominator out of these two, and then figure out how to get the common denominator and add these things, he could write this as the integral of one longer rational expression like this. So my dad did this for me, and I came back from whatever I was doing, and he probably said, "Oh, Chris," because he was a physics major in college. He doesn't remember anything, but he said, "Oh, Chris, I helped you out. You had these two integrals, and I combined them into one bigger integral." I said, "Dad, but I mean, these were really easy to do, and I could have done these in a couple of minutes, and now you combine them in this one big one. So can you just give me the old piece of paper, um, so I could do the two original ones?" And my dad said, "Well, I used that to light the grill, because my dad was going to make steaks." So I thought, oh no, now I've got this mess, this huge rational thing that used to be two integrals, but my dad, in his attempt to be helpful, combined them into one rational thing. All right. So the integral that he gave me, so the complicated integral, looked like this. It was the integral of 3x minus 1 over x plus 2 x minus 3 dx. So that was the integral that my dad came up with, that I knew came from two simpler integrals. So I'm just going to work on the integrand. So I'm just going to focus on this part here. Focus on the integrand. All right. And we'll go over here. And so our integrand was, or is now, it wasn't that complicated, but 3x minus 1 over x plus 2 x minus 3. Now, I'm not much of a detective, but I guessed that my original two fractions had denominators of x plus 2 and x minus 3. And that's why the common denominator, the lowest common denominator, became x plus 2, x minus 3. So I'm going to guess that originally this came from a something over x plus 2, and I'm going to guess that that was added to something else, b over x minus 3. So my dad came up with this, but I think that originally it had to do with two simpler fractions like this. All right, well, I know this, and first of all, fractions are a bit of a hassle, so I'm going to multiply through by the lowest common denominator. So the 3x minus 1 just stays that, and this equals a times, well, the x plus 2 will cancel, so that just remains x minus 3, and that'll be b times x plus 2. Okay, so now this is some equation with an unknown a and an unknown b, but my a and b will help me get back to my original fractions. Well, this should work for any x, so I'll make a note. Should work for any x. So if I said, what would be a convenient value of x to use here? Let's see, actually, I'm going to pause for a second to make sure I do this the right way. Okay, so I'm going to distribute this a little bit, so I'm going to rewrite this as 3x minus 1 equals, let's see, ax minus 3a plus bx plus 2b. And I'm going to rearrange it again. So this, actually, I'm going to go full screen here. So 3x minus 1, so I'm going to combine my x terms here, so it really becomes a plus b times x, and then a plus b times, let's just combine these here, so it'll be a negative 3a and plus a 2b. So I could combine this again, and well, okay, so let me explain this a different way. So if I look at the parts that multiplied by my by the x, so 3 times x has got to equal a plus b times x. So from that, I can say that a plus b must equal 3. And I can also say that negative 3a plus 2b has to be equal to negative 1. So that's saying that whatever my linear term is, the coefficient on the linear part of my equation, the part that's multiplied by x, must be like this, and then the part that's multiplied by a constant, this part, must be the same as this. I was going to tackle a different technique here, but I just remembered that this is the easier way to do it. Well, so what I can do now is say that b, so I'll just solve for b here, b equals 3 minus a, and then I'll stick this in over here, and so I get negative 3a plus 2 times 3 minus a equals negative 1, and then I can simplify this, and I get negative 3a plus 6 minus 2a equals negative 1, and then this combines to be a negative 5a equals, subtract 6 over there is negative 7. So a equals 7/5. And then what I can do is take that 7/5 and stick it back in over here. Like that. So b equals 3 minus 7/5, which equals 15/5 minus 7/5, which equals 8/5. Okay, so that's just, I mean, old school algebra going on there. And then when I put that all together, I know that my original, where am I? My original integral must have looked like this. So my dad put these two things together and got 3x minus 1 over x plus 2 x minus 3 dx, and that must equal to the integral of 7/5 over x plus 2, because that's what my a was, dx, plus the integral of 8/5 over x minus 3. Okay. Now, those are both relatively easy integrals to do. How do we do those? Well, this is 1 over something, right? And the integral of 1 over something, as we learned last semester, is the natural log. So I'll leave that to you guys, because the algebra is really kind of the tricky part here. Let's take a look at another example. And so for those of you who are thinking, oh man, this trig is killing me, this trig is killing me, there's really not much trig involved in these. There could be, but there's not right now. And but the algebra is just it's kind of a bookkeeping fest. So what happens if our common denominator that we're looking at has a repeated root? For instance, I'm just going to skip the skip the integral stuff and just focus on the fractions. If we wanted to decompose x over x minus 3 squared. Let's say we want to decompose this thing. And I'm going to say that that's going to equal x over x minus 3 squared equals a over x minus 3 plus b over, well, what's the other part? X minus 3 squared. Now, why did I make this one squared? We know this is x minus 3 times x minus 3, so why don't we make this x minus 3 and x minus 3? Well, the reason we do that is that if my original, if my two partial fractions both had common the denominator x minus 3, then we could just add them. It would just be a plus b over x minus 3. But somehow whoever did this favor for us decided that the common denominator has to be x minus 3 squared. So we have to deduce that the two partial denominators were x minus 3 and x minus 3 squared, and that led us to the common denominator of x minus 3 squared. Okay. So in this case, I'm going to multiply through by x minus 3 squared again. So this will give us x equals, well, there will be one x minus 3 left here. So that's a times x minus 3 plus, and the x minus 3's cancel out here, b. And again, and this is the technique I was thinking about earlier, x could be anything, and this should still work, right? So the game here is to pick a convenient x. So for instance, what would be a really convenient x? What if x equals 3? So if I do that, this becomes 3 equals, oh, look at that, that goes away. I like zeros, so that just leaves me with a b. So that's pretty nice. And then what if I pick another convenient value of x? I don't know, something easy to work with. How about x equals 0? And then this becomes 0 equals a times, well, that becomes negative 3a plus b. But I know what b is, so this becomes, let's see, 3a, well, I can just write this, 3a equals b, so that means that a must equal 1. So I can rearrange this and say that my original integral goes to, or my original fraction, because I didn't really do these as integrals, becomes 3 over, well, let's see, a is 1 over x minus 3 plus b is 3 over x minus 3 squared. All right. So, and again, think about how do we integrate these things. You know, what technique that's in our arsenal do we have to solve these types of integrals? All right, let's do another example here. And basically there's a few cases that we have to understand, and then we'll be able to do all these. So another example is, and again I'm just going to work on the integrand. What if we have something really nasty, like say 3x squared minus 8x plus, how about 13 over, and let's have an x plus 3, and let's have a repeated one in here, x minus 1 squared. Okay, so here I have this repeated root, so I probably had an x minus 1, I probably had an x minus 1 squared, and I probably had an x plus 3. Alright, so I'm going to say this whole thing equals I'll get rid of my easy one first, that's just over x plus 3. That was one of my original partial fractions. Plus b over, let's call that just the x minus 1, the linear denominator. And then the c now to account for x minus 1 squared. Wow, what a mess. Well, I'm going to distribute, here's this equation, I'm going to multiply through by this lowest common denominator that we found, so my left side of the equation just becomes 3x squared minus 8x plus 13, and the right side, well, it'll be the x plus 3's cancel, so it's just x minus 1 squared, and then plus here, one of the x minus 1's will cancel, so it becomes b times x plus 3 x minus 1, and then c, both the x minus 1 squareds will cancel, so I'm just left with x plus 3. Okay, and again, this works with any x. So the game becomes just pick convenient values of x. Well, one convenient value of x that'll make a lot of stuff go away is x equals 1, because that makes this go away and that makes this go away. So that's the first one I'm going to do. X equals 1. All right. So now I have 3x squared, which is 3, minus 8, which is negative 5, plus 13. That'll just become an 8. Right, is that right? 3 minus 8 is negative 5, plus 13 is 8. Yeah, that's right. Equals, well, this goes away, so all I'm left with is 4 times c. And that leads to c equals 2. Well, that's nice. I've got one of them already, so I'm going to put kind of a dotted dotted box around that one because that's a pretty important step. What's another nice one? Well, -3 also will make two things go away. So I'm going to pick x equals -3. And so that means, well, this becomes a hassle. 3, 9, so that's 27 minus 24 plus 13. I'm going to say 64 there. Equals, and then all that's left is this, and that's x equals -3, so that's -4 squared, which is +16, so that's 16a. Well, that's convenient, because then this goes away, and this goes away. So this gives me a equals 4. Alright, good, good. And then, well, I picked everything that makes stuff go away, so now I just pick something easy, and my favorite number that's easy is 0. And then, so we say this is all 0, so this is 13 equals x minus 1 squared, so that's just a, and so 0 is 3, minus 1, -3, so minus 3b, and then plus 0, so that's just 3, so it's 3c. So I know that much. But the thing is, I know what a and b are, or I know what a and c are. So 13 equals 4 minus 3b plus 6, and that means 3 equals, so that's 10, so 3 equals -3b, so that finally gives me b equals, I think, -1, and so now I've got this thing. Alright, now finally, holy cow, this original fraction up here, right, breaks down into, and if we think about trying to integrate this thing, holy cow, this is cubic, there's a square up there, we have all sorts of x's and 13s and stuff all over the place, what a mess. But this will break down into, let's see, a is 4 over x plus 3, plus b is -1 over x plus 3, x minus 1. Oh, no, just x minus 1. And then finally, let's see, c is 2 over x minus 1 squared. So here is our final answer. I don't know, I'm having trouble writing today. Some days this writing on this tablet is surprisingly hard, and this is a nice tablet as tablets go. So there we go. How did this one work? We had one unique and then one repeated root. So we had to have the unique one and then both versions of this repeated root there. All right. Now those were pretty easy, but unfortunately they get a little more tricky. So we're going to do an example. Where am I? Where's my pointer? Example. We'll look at a quadratic factor. Okay, and this example is going to look like this. We've got 6x squared minus 3x plus 1, and that's going to be all over 4x plus 1 and then x squared plus 1. Okay, so this one, x squared plus 1, if it was x squared minus 1, we know that's x plus 1, x minus 1. But this is x squared plus 1, so we can't really break that down into anything cleaner. So we'll kind of take the same approach. We'll put the a over 4x plus 1. But as it turns out, for the quadratic factor here, we've got to do something a little bit more special. and we're going to say if it's quadratic on the bottom, it's linear on top. So we'll call that bx plus c. And then the bottom here is x squared plus 1. Okay, and now the process becomes very much the same. We'll multiply through by this, so that cancels out, so I get 6x squared minus 3x plus 1 equals a. The 4x plus 1 cancels, so I've got a x squared plus 1 plus, and then bx plus c times this 4x plus 1 over here. Okay, so now this one isn't quite as clean, but I realize that if I pick x equals negative 1/4, this goes away. So at least I can get rid of my b's and c's with x equals negative 1/4. All right. So plugging this into here is a real hassle. So let's see, that's 16ths. 6/16 minus 3/4 plus 1. All right, I'll just write this out. So 6/16 minus, actually plus 3/4 plus 1 equals, and then squared that is 16ths, so that's 16/16 plus 1/16 is 17/16. Jeez. But thankfully all this stuff goes away. Alright, so this is 12/16, 18/16, and then 34/16. So 34/16. Oh, that works out alright. Equals 17/16 a. So from that I get a equals 2. Alright, so I've got one of them. And then now it, we got to get b out of this. Well, let's see, what might be, how'd that get out of there? Is there anything else easy that could make stuff go away? Not really. But what if I pick x equals 0? That's when in doubt, pick an x equals 0. How does this work out for me? When x equals 0, well, that goes to 0, and that goes to 0. So that just becomes 1 times c. Oh, so that just becomes c. That's nice, because the b goes away. So, and then that's a. So how does that work out for me? But I know a is 2. Oh, okay, so this is alright. So I could say if x is 0, 0, 0, 1 equals, this is just a, so it's just 2, plus, and the only thing I have left here is a c. So 1 equals 2 plus c. Oh, that's nice, because then that gives c equals negative 1. Sweet. Alright, and then now all we need is b, so we pick a, so we only have one variable left, right? We know a, we know c, the only thing we don't know is b, so I'm going to pick an easy, x. How about x equals 1, because that's easy to plug in. So 1, 1, 6 minus 3 is 3 plus 4, so it's 4. That's a 4 equals 1, 2a, I think. Yeah. Oh, that's 2. 1, 2, 4. Because I know a is 2, so it's 4. And then put a 1 in here, and that's c is 1. So that's b plus 1. So that becomes b minus 1 times 5. Alright, so how does this shake out? 4 equals 4 plus 5b minus 5, get everything over there. Plus 5 is 9, subtract 4 is, well, that's 5, so 5 equals 5. So this gives me b equals 1. Okay, so now I'm done. I've got this whole thing. And I now have this equals the integral, this whole thing. Will become 2, right, because it's a over 4x plus 1. And let's just integrate this thing, see what happens. So it becomes 2 over 4x plus 1 dx plus the integral of bx plus c, so 1x minus 1. So that's just x minus 1. Over, that's not a very good over, x squared plus 1, okay, dx. So this, if this were my original integrand over here, if this were my original integrand, it would break down into two integrals that look like this. So let's actually go through and try to integrate this one here. I'll rewrite this again as, let's see, this one should be pretty easy, because if I just do a u, well, I'm gonna break this up. I'm gonna say this is the integral of 2 over 4x plus 1 dx plus, now I'm looking at this one, u substitution comes to mind, so my du equals 2x. Right? If this is a u, then du equals 2x, so I could put a 2 up here, but I've got this extra stuff here. So I'm going to break this into a couple different integrals. So it's going to be x over x squared plus 1 dx plus, actually minus, the integral of 1 over x squared plus 1 dx. Alright, so are we making any progress with this here? I lost my pointer. Here it is. Okay. So this one we can just say that I'm going to do this in different colors here to kind of keep track of stuff. I'm going to say that u equals 4x plus 1, so then du equals 4 dx, right? So I don't have a 4 dx, I only have a 2 dx, so I'm going to put another 2 in here, which means I have to put a 1/2 out here. And now this becomes the integral of 1 over u du. Okay, piece of cake. And let's look at this one here. How's this one going to work out? Same deal, except this time I'm going to use a v equals x squared plus 1, and then dv equals 2x dx. Well, so I have an x dx, but so I just need a 2 here, and which means I just need a 1/2 there. All right. And so lastly, this one, orange. So if I said u equals, or 2vw equals x squared plus 1, and then dw equals 2x dx, so I need a 2x, or at least an x dx here, but I don't have an x dx available. So what am I going to do there? This is kind of, well, you know what I'm going to do? I'm going to ignore it for now. That's what I'm going to do. So let's just look at this one. And so this becomes the integral of 1/2 the integral of 1 over u du, which equals just natural log. So natural log of u, and so that really becomes, well, it's 1/2, so that's 1/2 natural log of u is 4x plus 1. And then this one here is same deal, 1/2 u du. So this will become 1/2 natural log of x squared plus 1. Alright, but we still have this one. We've got this x squared plus 1. So whatever do we do? Oh, I know. What if we said that x equals tangent of theta? Alright. So now we write that this and then dx derivative of tangent is secant squared, right? D theta. So we thought we were going to avoid trig all day, but no such luck. Now this becomes 1 dx, which is really secant squared theta d theta over the square root of tangent squared plus 1. Right? But I know tangent squared plus 1. Oh, that's not the square root though. Get it out of there. We're so used to doing that. Ooh, nice work with your eraser there, Dress. So tangent squared plus 1, which is really secant squared. So it's really secant squared over secant squared. So this just becomes the integral of d theta. Now we talked about this one yesterday. So this just equals theta, right? But what is theta? Theta is the arctangent of x. Like that. Alright, so we have this, and I'm going to erase this equal sign, because really what we're doing is subtracting that. So our final answer for this integral, which involved a lot of tools, is 1/2 natural log of 4x plus 1 plus 1/2 natural log of x squared plus 1 minus the arctangent of x. Now this 1 over x squared plus 1 is going to show up a lot. Alright, and that's going to become a really useful integral. So you might as well kind of commit this to memory, that this is going to be arctangent. 1 over x squared plus 1, integrate that, and that becomes arctangent. This, I know someone's going to call me on this, plus c, becomes the final master answer for our partial fraction decomposition. And I'm going to finish the lecture on that huge example, and I look forward to seeing you guys in class.